This problem says to factor and simplify. So we have this large expression here with all kinds of trig going on, and we need to factor and simplify. So factor means like this is like a standard form, and we need to factor it into factored form. Some people might just be able to look at it and realize that what would multiply to make this? Well, it's cosecant to the fourth power, so we'd need two of them here and two of them here if we kind of split them evenly. Same thing here at the end, the last term, cotangent to the fourth power. You'd need like, cotangent square and cotangent square. And it looks like there's a negative in there, so we're going to need some negativeness involved. If you need to, we can always use the area model to help us out. So let me draw a nice big area model because these expressions are rather complicated. And so you remember for the area model, we could put the first term in the first box. That's cosecant to the fourth. And the last term in the last box, that's cotangent to the fourth. And then if we multiply those, this diagonal, well, really that would just be cosecant to the fourth times cotangent to the fourth. And of course, that's part of our diamond problem. What multiplies to make those two things, but actually adds to make this? And let's see if I can squeeze that in there. It's negative 2 cosecant square and cotangent square. Barely fits into there. So that's that middle term. All right, so what multiplies to make that but adds to make that? Notice they both have a bunch of these cosecants, cotangents. It looks like we need a cosecant square and a cotangent square, but we end up with two of them when we add them together. So it means there must be one on each side of these. Since it's negative, it's actually going to be negative 1 of the cosecant square x cotangent square x. I don't need the 1 there, but I'm going to put it there just so you can see that one of them and one of them makes two of them when we add them. And then same thing here. So these two things, this left side, this right side, would add to make negative 2 cosecant square cotangent square. But if we multiplied them, that'd be negative times negative is positive, and of course if we have squares and squares on both of these, it ends up being to the fourth power. So that's actually it. These two pieces, these two crazy things here, that's what's going to go in these boxes here. So now let's see if we can write small enough and neat enough to fit into there. So it's actually going to be, well, let's keep it blue. It's going to be negative 1. I don't need the 1, but I'm just putting it there. Cosecant square, cotangent square. All right. Sorry if it's difficult to read. And the other guy. So one of these on one box, one of these on the other. They happen to just be the same thing. All right. There. Now we need to check out the area model and find the base and the height, because that's what this is going to be. One will be the base and one will be the height. Base times height. That's factored form. So if I look at what's in common here, it looks like it's the cosecants. And this one has 4 to the fourth, and this one is square, so 2 of them. So I would say that what's in common is actually 2 of them, or square. And then over here, what's in common? Well, definitely it has cotangents and cotangents, but this has a negative. And if we can kind of think ahead here, we're going to have actually a negative thing here and a negative thing here to multiply to make this positive. So you'll see what I mean if you didn't recognize that. But I'm actually going to say there's technically a negative in this box. So I'm going to say a negative is in common and a bunch of cotangents. In fact, it looks like it's 2 of them, cotangent square. And actually, similarly, this direction. They definitely have cosecant squares. This has 2 square. This has 4 to the fourth. But in common is 2 of them, or square. And then same thing here. I'm going to say that there's actually an invisible negative in this guy. You'll see what I mean in a second. I'm going to say that there's a negative in common. And of course, there's a whole bunch of cotangents in common. All right, if you didn't recognize that, check it out. Negative cotangent square times the other negative cotangent square actually makes positive cotangent to the fourth. And then, of course, if I multiply this base times height, we get the negative cosecant square, cotangent square. And, of course, if we multiply these two to get this top left box, that would just be cosecant to the fourth. And if we just check them all out, when in doubt, test them out, they all seem to work. So there's our base and there's our height. Notice they're actually just kind of the same thing. It's a duplicate of each other. Let's see if I made my factors large enough to write neat enough. So there's the base, and then the height is actually the same thing. All right. So we factored it. It said factor and then simplify. Well, okay, so we got our factors, now what? We got to simplify. Well, you may have noticed I have over here a piece of the cheat sheet that we have with our identities. And actually, if I scroll over, some of these identities look kind of appropriate. Like, we have a whole bunch of cosecant squares and cotangent squares. That reminds me of the Pythagorean identities. And actually, it kind of looks like this one with cosecant square and cotangent square. The only thing is it's got 1 plus cotangent square. What I can do is I can take that, in fact I'll move it down here, and I can sort of modify it. I'm going to do a modified version of it. And I'm actually going to subtract cotangent square from both sides. And then I get 1 on the left, that's it. And then now on the right side, I have cosecant square minus cotangent square. And that looks familiar. That looks a whole lot like what we got going on in our problem. So this cosecant square, cotangent square minus cotangent square can actually just be replaced by 1. And that's actually what we have back over here. Cosecant square minus cotangent square. That's technically just a big old 1 using the Pythagorean identity. In fact, so is this one. It's just a giant 1 using the Pythagorean identity. So really, you know, here's our complicated math. 1 times 1, and that just gives us 1. That's our answer. This can simplify. After we factor and simplify, it turns into 1. So that one's done. Let's check out the next example here. This one also says factor and simplify. And this one also looks like it's in standard form. The only thing I noticed though when I look at this standard form is everything has kind of like a factor of 3 in it. I'm actually going to like pull out or factor out a 3 out of this thing, and let's see what's left over. What's left over here is cotangent square of theta, because 3 times the cotangent squared would equal that. We're like unmultiplying. Plus, and then actually 3 times something would give me this. That would be 3 times 2, but it also has a cotangent. Plus, and then this, if I pull the 3 out, well, it's actually 3 times what would give us that? I'm unmultiplying or factoring. Of course, that'd be 3 times 1. So now I've factored out the 3, and here's what remains. So let's kind of just ignore that 3 because we already factored it out. It's 3 times this whole thing. But this is like another, maybe simpler, standard form. So my thought is maybe I can factor this thing into like, you know, a base and a height, base times height. And some people might see it right away that this is actually just a cotangent times a cotangent, and it's also just a 1 times a 1, and the middle will work out nice for that. But if you don't just see it, let's, you know, use the area model. When in doubt, write it out. I'm going to put the first piece in the first box. I'll put the last piece in the last box. Of course, we multiply this diagonal, and that's just 1 times cotangent square of theta. And that multiplication is part of our diamond problem. What multiplies to make this, but has to add to make that middle term that we haven't used yet. So that middle term is just 2 cotangent of theta. All right, so what 2 things multiply to make this, but add to make this? It's actually just a cotangent times a cotangent multiplies to make square. And then a cotangent plus a cotangent adds to make 2 of them. So really it's just a cotangent theta and a cotangent theta. And that's what goes in these 2 other boxes. So we've sort of filled in our area model. Now we just need to you know, find the base and the height of this thing, because there's our base, there's our height, that's our product. Of course, what's in common here would just be a cotangent. What's in common here? Well, it doesn't seem like there's anything in common unless I mark that as a 1 cotangent and a 1 cotangent. Kind of like what I did on the other problem up above. I did put the 1s there. And here I could put the 1 there to see it really is just 1 in common. So a positive 1. In fact, same thing across here, just cotangent in common. They only have 1 of them in common. This has 2 cotangent square, but this only has 1 of them. So same thing here, a 1 is in common, just like our base. And there we go. Actually, the base and the height are exactly the same again. So my base is cotangent theta plus 1, and my height is actually cotangent of theta plus 1. Now, in terms of an identity, this actually doesn't look like Pythagorean identity because it's not square. What I could maybe do is turn cotangent into sines and cosines, but you know what? I don't think I want to do that. What I might just do to simplify it is notice that those two are the same. So a simpler way to write that would just be 3 times cotangent of theta plus 1 square. I'm going to say that that's good enough, just because I don't recognize any other particular special identity to make it super duper nice. But that looks good enough for me. So there we go. I've factored and simplified each of those expressions.